G'day and welcome to my short introduction to logarithms. There'll be a series of videos here which will introduce the idea, and I'm going to really hammer home the concept and how it's a reversal of some procedures that you've done before. So first of all, logarithms, it's a bit of a scary word, but it really doesn't need to be. It can be quite simple if you've got the background concept sorted. Let me start with a little bit of an example. Imagine if I had, for example, x plus 2. It's just a common take a number, add 2 to it. And you will have learned through the process of algebra, and even earlier, that the way we reverse a plus 2 is we subtract a 2. So that's kind of an opposite, equal and opposite relationship there. Now, a little bit more abstractly, at some point you learn about squaring numbers. So let's say, for example, 4 squared, which is equal to 16. So you learn all about how if you square 4, it means 4 times 4, you get 16. Now that's not so abstract, but what happened is at some point somebody said, 16. I wonder what that number was before it was squared. I wonder what number was squared to get to 16. And that's where we invented this actually quite abstract idea of a square root. So when you first learnt that, it really doesn't come that naturally. And it's a background working thing because you have to think to yourself, right, so what number did I multiply by itself to get to 16? That's what a square root is. And this is the problem when we get to logarithms. Now you'll know that this is 4. You'll know that we worked that backwards. And you'll also know that square root and squaring numbers, so square root x and x squared, well, they're equal and opposite operations. So they do the opposite thing. Of course, if you square a square root or you square root a square, then they kind of cancel each other out in a sense. So we get the same thing, but with a new problem. So let's have a look at our new problem up here. And I'll hide behind my little square roots. So, I've got this problem. It's a common exponential. You've done a few of these. 2 to the power of x equals 8. Okay, so happy days there. 2 to the power of x equals 8. We don't need logarithms for this because we know 8. Well, another way of writing 8 is 2 cubed. So 2 to the power of x equals 2 cubed. And so that means that x must be equal to 3. That's equating our powers. You can see the indices, x here, 3 there, 2 to the power of something equals 2 to the power of something else. The something must equal the something else. It's the only way to make it work. But what about if we had a question like this? 2 to the power of x equals 7. This is where we have a problem. Because 7 is not a power of 2. Now I can play around with this. I know 2 squared, that's equal to 4. And 2 cubed, that's equal to 8. So let's try 2 to the power of 2.5, that's equal to something, say 6.5 or something like that. A bit small, let's try 2.7, a little bit small again, 2.8. Get closer and closer, a bit of trial and error, that'll work. It'll definitely work, particularly if we've got a calculator, but we want a more efficient way. So we look for a more efficient way, and that is to create a reverse operation. So what we've actually got is a reverse operation here. Now I'm going to give you a bit of a lowdown, and then in the next video we'll explore the idea of the logarithms in an algebraic sense. So the reverse operation here, the introduction of logarithms is 2 to the power of x equals 7 can be written in your calculator as log base 2 of 7 equals x. And by way of a one sentence introduction before the end of this video, this means 2 to the power of what equals 7. You didn't think I'd run away without giving you an answer, did you? Well, if you evaluate this on your calculator, you get x is equal to 2.8073549922. It is an irrational number, so it does go on and on, but we're going to stop there at that 22 because that's all the calculator has given to me. And those number of decimal places there is pretty adequate. All the best.